Yo, yo, yo. Welcome to the continuation of the gas laws. So you guys should have covered um, Boyle and Charles' law. Today we're going to cover Gay-Lussac and the combined gas law. So with Gay-Lussac, he wanted to take a look at temperature and pressure. So he decided to conduct 4 trials. Say we have a container. We heat up the container that contains some gas molecules. As we heat up the container, these gas molecules begin to move faster and faster, and that is the definition of temperature, y'all, the average kinetic energy. So if we increase that temperature, we know these guys are moving faster. So that's what's happening here. In each trial, Gay-Lussac increased the temperature. And then notice a change in that pressure as well. So he recorded a pressure of 0.910 for trial number 1. And then for trial number 4, as that temperature increased, pressure increased to 1.37 atmospheres. So as temperature increases, pressure increases. This makes sense. In our drawing here, these molecules are moving very, very fast, hitting the sides of the container a lot more. And so that's the definition of pressure, if you recall from yesterday, is the force of collisions on the side of a container. So the more collisions, the higher the pressure. And just like yesterday, we can't multiply these two numbers and expect them to equal each other. So we have to divide. So I have pressure divided by temperature, and once I do that, y'all, if we take a look at the numbers, it is relatively constant. So I want you guys to take a look at your graph on your notes, and I want you to label the axis. Again, pressure is on the y-axis, temperature is on the x-axis, and it's because we can't control the temperature. So as we increase the temperature, more collisions on the side of the container occurs, meaning that there is an increase in pressure. So you should see a line like so. Now I want you guys to write down the relationship between pressure and temperature. So the pressure and temperature of a gas is directly proportional. Or if, again, the word the same helps you out, you guys can write it down as such. So this occurs at constant mass and volume, and like mentioned yesterday, we're going to talk on that a little later on. And if temperature increases, then we know pressure increases as well. And I could use variables and arrows just like the other laws. So let's write it down. Underneath this, here, y'all, the pressure and absolute temperature of a gas are directly proportional. I want you guys to write down temperature increases, pressure increases. Or if temperature decreases, we also know that pressure will decrease because there will be less collisions on the side of the container when it's cooler, because it's the opposite of heat them up, speed them up, cool them down, they'll slow down. Okay. Now let's set the constants to 2 different conditions. Those are conditions 1 and then conditions 2. So if I cross multiply, I get rid of the fraction, and I get my Gay-Lussac's law or equation. P1 times T2 equals P2 times T1. So let's try our problem here. Again, we're going to use the guess method. Guess method, I'm going to label it up here, and I'm going to check it off as I go through each step. So for G, it stands for givens. So we have to read our problem in order to find our givens. U stands for our unknown, what we're looking for. E is applying the correct equation. S is for substituting our values. And the final S is to solve. So let's do that. Let's read first to get our givens. The pressure of a gas is 756 torr. So I'm going to label it as I go. So underline, that says pressure, so that's going to be my first set. Pressure 1 at 23 degrees Celsius. So that Celsius tells me temperature, so this is T1. I know it's my first set and that these two numbers are paired with each other because it has a connecting word like at. At what temperature? Ooh, so this looks like our unknown. Okay, so this right here, T2, will the pressure be 560 torr? So 560 torr, this is P2. So now let's go over G, our givens. I'm going to copy it down from my problem. So P1 is 756 torr. T1 is 23 degrees Celsius, but I can't use Celsius. Remember, whenever we have the gas law problems, we must use Kelvin. So in order to convert from degrees Celsius to Kelvin, I need to add 273. So I'm going to use a calculator to do so. So 23 plus 273 gets me 296. So 296 Kelvin. My pressure 2 is 560 torr. And then I'm looking for temperature 2. So now I've completed the given. I've also know that temperature 2 is my unknown. So that's also done. Next step is to get the correct equation. So the equation is P1 T2 equals P2 T1. So I have my equation. I need to solve for T2. So I need to isolate T2 or get it by itself. And in order to do that, I need to divide both sides by P1. P1 on the T2 side cancels out. So I'm going to rewrite it just to make it look nicer. So P2 T1 divided by P1. So I have my variable isolated. The next step is to substitute my values. So that's what I'm going to do. I'm going to plug in my values. So P2 is 560 torr times T1 is 296 Kelvin divided by, and P1 is 756 torr. So I'm going to use my calculator in order to solve this. Again, using the method Ms. Flores showed us, we click on this here to get a fraction. So I have 560 times 296, and then on the bottom 756. And in order to prevent myself from not getting a decimal answer and just getting a reduced fraction, I'm going to add this decimal here. This will automatically give me a decimal answer. So I see it, 219.2. So I'm going to round it to the appropriate sig fig. I look at the numbers I use in my problem here and use the fewest sig fig. So the fewest would be 3. So I'm going to be I'm keeping this, and since there's a 2 there, I'm not going to round that 9 up. I'm going to keep it as is. So our final answer would be 219 Kelvin. I know it's Kelvin because torr on top, torr on bottom cancel each other out. Okay. Okay, let's move on. So we have the combined gas law. The combined gas law is what you guys would think it is. And we have to combine all three together. Whoa, whoa, whoa. So we have P times V equals K. We also have V divided by T equals K. And last but not least, P divided by T equals K. So if I were to merge all of these equations together, I would get something like this. PV over T equals K. But since K is a constant, I can set it equal to another set of conditions. So I can, in turn, have condition 1 equal condition 2. So again, this is the combined gas law, but I don't like fractions. So I'm going to cross multiply. And when I do, I get P1 V1 T2 equals P2 V2 T1. So that's what I want y'all to write down. This is the combined gas law. So it has all three variables and the relationship between the three: pressure, volume, and temperature. Moving on to the next concept. So there's a certain condition called standard temperature and pressure. So I want you guys to write that down: standard temperature and pressure underneath your combined gas law equation. And in parentheses, that standard temperature and pressure is STP. So write down STP, y'all. So STP. This presentation might be a little confusing because it looks like it's color-coded, but it is going in this direction here, okay? 0 degrees Celsius or 273 Kelvin. So for temperature, standard temperature, I want you to note that it is 0 degrees Celsius or 273 Kelvin. For standard pressure, I have 1 atmospheres or 101.32 kilopascal. So these are 4 numbers you guys should know, and it all goes with STP. We're going to see how STP works on the next slide. So again, we're going to use the guess method. So our givens, we get our givens from reading the problem. So a gas occupies 7.84 centimeter cubed. A centimeter cubed tells me that this right here, y'all, is my volume. So I'm going to denote it as volume 1 at 71.8 kilopascal and 25 degrees Celsius. So I have this here, which is going to be my P1, and temperature is T1. Find its volume. So I know to find the volume, that's going to be my unknown, so I'm boxing it, at standard temperature and pressure. Whoa, whoa, whoa. Mr. Tran, I don't see a second set of temperature and pressure numbers. Well, STP tells you that you have to use 0 degrees Celsius or 273 Kelvin, depending on what unit you have, and 1 atmospheres or 101.32 kilopascal. So let's put in our givens first. Let's complete G. So P1 is 71.8 kilopascal. Volume 1 is 7.84 centimeters cubed. Temperature 1, 25 degrees Celsius, but we have to add the 273. And when I do, I get 298 Kelvin. Pressure 2, again at standard temperature and pressure, I need to know what that unit is. I see that it is kilopascal, so I can't use 1 atmospheres. I must use 101.32 kilopascal so that the pressure unit can cancel out. Whatever is in my given, y'all, I must use for my second set if it's not stated. It's not stated in STP, so I need to use, again, whatever is given to me. And then volume 2 is my unknown here. And temperature 2 is at STP. We never use degrees Celsius, so we always use Kelvin. It is 273 Kelvin. So I'm done with my guess, or my G of guess. For my unknown, again, in our problem, is asking for volume, so V2. So my unknown is also done. Now I need to use the equation. The equation, you guys should have written down, is P1 V1 T2 equals P2 V2 T1. I'm boxing the one I'm looking for, and I need to get that variable by itself. So in order to do that, I need to divide both sides by P2T1. Once I do, it cancels out. So I'm going to rewrite it so that P2 is on the left-hand side and the rest. P1, V1, T2, P2, T1. So my equation is done. I am going to be substituting my values. That's the first S. So P1 is 71.8 kilopascal. And times V1 is 7.84 centimeters cubed. Times T2 is 273 Kelvin. Divided by P2, 101.32 kilopascal times 298 Kelvin. So I'm going to use my calculator to solve this, y'all. So I'm going to use the fraction function. So clicking here. Now I have 71.8 times 7.84 times 273. And I'm going to click for my bottom fraction times 298. So I have decimals, so I'm just going to click on enter, and I get this answer here, 5.08969. To round to my appropriate sig fig, I always count the fewest, or see which number has the fewest sig fig. So that number to me looks like to be 3. So I'm going to round my answer to 3 sig fig. So I'm going to highlight it. I have 3 sig fig. Since this is a 9, I'm going to round that 8 up to a 9. So my answer is 5.09. To get the unit, I need to look at what units canceled out. Kilopascal did. Kelvin did. The only one that's not canceled out, centimeters cubed. So substitute and solve. So let's review. We covered this during your kinetic molecular theory notes. So let's go over it again. Particles in a real gas have their own volume and attract each other. But under the assumption of the kinetic molecular theory, gases are considered to be ideal, meaning they follow what we've learned from the kinetic molecular theory. So they don't have their own volume and they don't attract each other. Okay, so those were postulates y'all should have known. Gases behave most ideally at low pressures, high temperature, and in nonpolar atoms. And again, this helps with the whole assumption that they don't attract each other. With low pressures, there are more space for the molecules to move around. High temperatures mean that they are moving very fast. So again, there's definitely no attraction at all. And the nonpolar atoms have no partial charges to even have any attractions. Continue on with our characteristics of gases. So the characteristics of gases here assumes the kinetic molecular theory postulates. So our first one says gases expand to fill any container. Again, and that's due to random motion, and there's no attraction or making these gas particles stick next to each other like the other states of matter. Gases are fluids, like liquids. Fluid is defined as being able to flow, move past each other. So again, key characteristic there, no attraction. So these gas molecules pass each other without sticking or having any sort of attraction towards each other. Gases have very low densities. So if we remember density is equal to mass over volume. So it's assumed that, again, gases have no volume, so there's just a lot of empty space in between. So very, very low density. Last but not least, y'all, gases can be compressed. Again, due to the assumption that it has no volume, just a lot of empty space. We can close that empty space as seen in this picture here. This is before closing that empty space. You guys can see a lot of space, but once the piston moves down, notice that the number of gas molecules didn't change there, but the space that these gas molecules occupy did. And so they're all very, very close to each other. Not a lot of room. That's compression, y'all. Taking away that available space and reducing the amount of room that certain particles can move. Last but not least, gases undergo diffusion and effusion. And this is the postulate where it states that gases move in random linear motion, right? So with diffusion just simply means disperse. So one way I like to think about it is a perfume bottle. You spray the perfume, and that perfume will spread, and if you start out from one end of the room, it will eventually reach the other end. So diffusion, dispersing. So disperse. Effusion is simply a gas particle or molecule passing through a tiny opening. So this is an example of effusion, passing through an opening. Okay, y'all, that's it for today. Have a good one.